The main objective of this lesson is to establish the relationship between the derivatives and graphs. First, let's explore the intervals of increase and decrease. We're talking about these two. When the derivative is positive, the graph should be increasing. When the derivative is negative, the graph goes down, decreasing. Here's a visualization. Clearly, this blue graph is going up, it's increasing. And pay a little bit of attention to this red line segment here. It's a segment of the tangent line. Now, what is the geometrical interpretation of the derivative? It was the slope of the tangent line. And look at this tangent line. This slope is positive. This red line segment is pointed upward as we move to the right. So slope is positive. That means the derivative is positive here. But not only at this point, take some other point here in this interval. Again, positive slope. Again, positive derivative. As a matter of fact, the same thing persists all the way, positive derivative. The only exception, at the end point, you may have something different, but then again, we are talking about the open interval anyway, so we are not going to consider the end point as at all. Anything in between, we have to have positive slope. In this case, the graph is increasing, as you can see. How about the other way around? Simple. Almost exactly the same. Well, I took pretty much exactly the same graph as a matter of fact, but even if we have very different graph, again the same kind of argument will work. Any point here, look at the tangent line, and the tangent line has negative slope, which means the derivative is negative. That means the graph is going down, decreasing. Some other point, as you can see, negative slope. Still negative slope. All the way, possibly except for the endpoints, but we are not considering endpoints. We are looking at the open interval anyway. In this case, decreasing. Now, what if you have derivative 0? Positive means increasing, negative means decreasing. So this will be neither increasing nor decreasing, at least momentarily. Here's one such point. It's called local minimum. Graph comes down here, hits the horizontal tangent, the derivative is 0, and now increasing, local minimum. Here's another point. Increase, the derivative is positive, so increase, and then hit this point, horizontal tangent, derivative is 0, and then decreases, local maximum. Here's another such point. Increase, hit horizontal tangent, keeps on increasing. That too is what you call critical point, by the way. That's something I'm going to explain a bit later. But this is neither maximum nor minimum. And also we can consider a situation the derivative does not exist at all, like this point. This kind of things are all called critical points, and that's the topic for 1.2, this next subsection. And let's continue our discussion here. What do you mean by a critical point? Either derivative is 0, like this or that, or derivative does not exist at all. The final case is really exceptional, so we usually do not consider it. After all, we are learning calculus, so you should be able to calculate all those derivatives and limits and so on. And in this case, you really cannot do any kind of computation. Okay, I take it back. You can do some computation, yes, but not a whole lot. Usually it's a good idea to consider these kind of points completely separate. Most of the time, we're going to consider these kind of points, and as you can see, they're all corresponding to the 0 derivative. The derivative of this horizontal line is 0, and those are the tangent lines here. You can classify them like this. A local maximum, as you can see, why it's local maximum, it's highest point among all those nearby points. Okay, this may not be the maximum because graph may continue and then may go up much further later on. Who knows? So this may not be the absolute maximum, but it is locally a maximum, so we call it local maximum. It goes like this. Increases and then hits this local maximum and then decreases. Or equivalently, positive derivative here, zero derivative and negative derivative. Increasing, critical, decreasing. That's when we have local maximum. That's when we have local minimum. Decreasing, critical, increasing. Negative derivative, zero, positive derivative. What about there is no sign change? Plus to minus, then maximum, minus to plus, then minimum. What if we stay plus? Increasing, zero, and then keeps on increasing. How about minus all the way? Negative derivative hits zero, again negative derivative, keeps on decreasing. In this case, we have no extremum. So here is a mini conclusion. If is differentiable, we can have this kind of conclusion. We're having local extremum at x equal to c. That means the derivative at c is 0 and the sign of the derivative at x equal to c, kind of like this. Change from positive to negative, change increasing to decreasing, or negative to positive, decreasing to increasing. No sign change, plus, keep on plus, negative, keep on negative. In that case, we do not have extremum. Of course, if f is not differentiable, all bets are off. Those are really special. Now keep those in your mind and let us move on to some exercise problems.